So this is 1D motion and how to do 1D motion. So from general understanding of math, right? We go back to our Calc 1 or, well, this is only in Calc 1 where you would see this. We learn that position is also called x, or displacement, right? Displacement, as we saw in the last video, is the delta x, the change in the position. So in Calc 1, and if you didn't say Calc 1, that's completely fine. In Calc 1, velocity, we derived and found that it was the change in position with respect to time, or simply algebraically, distance over time. And that gives you some value for velocity. Now, acceleration, same thing from Calc 1, we found to be the change in velocity with respect to time, or velocity divided by time, and that's the acceleration. Now, these are fundamental equations that Newton derived, and we can use them to solve for something called kinematic equations. Kinematic equations are equations to describe motion. So, kinematic equations will give you typically three different values, and that is a position, a velocity, and an acceleration. You also typically get a time out of the kinematics equations. This is how you describe any kind of motion of a particle in space. So how do we find the kinematics equations using these definitions that we have from Calc 1? Well, seeing that dx dt is equal to the velocity, we can move the dt term over here. This is an integrate, right? Basic integral. We have the integral of dx is equal to the integral of v dt. And we're left, because this is an indefinite integral, remember, so this would be x plus c, and then vt plus c. Now, because a constant, there's two constants on both sides, you can subtract the constant to this side and still some other constant. There's still a constant there. So you're left with the kinematics equation, x is equal to vt plus c. Now, what would this constant be? Well, that constant would be x naught, or the initial position. And that makes sense. Let's talk about acceleration. Same thing for acceleration. dv dt, we move the t over to this side, and we're left with dv is equal to a dt. Integrating on both sides, we have v plus c, right? Because the integral of dv is v, and the indefinite integral of a dt is at plus c. Moving the c over to the to the other side, same exact thing. We get v naught. We get v is equal to at plus v naught. So now if we want position out of this, well, we have this equation that we found right here, right? We can plug, or we can integrate both sides of this equation to find position, right? Because we said dx dt is equal to v, so integrating v, you're able to get some x position, some position of x. So that's what we're doing here. We integrate indefinite integral of v with respect to time, and the indefinite integral of the acceleration times time plus v naught with respect to time. We're left with x, right? Because the indefinite integral of v is x plus c is equal to at squared. That's the integral of t. This is t squared over 2. So at squared plus v naught t plus c. Same thing, moving the c over to this side, we have our x naught term. Now, these are the three main kinematics equations that you'll be using, but there's another one where you can plug it in, and you end up with this one here. It's just plugging something in. Same with here, you plug something in, and you're able to solve for it specifically without time. Is what the use of this one is that it doesn't have a time variable in it. These are the main ones that you'll be pretty much given on every kinematics physics A test. These will all be on your formula sheet. You're going to be needing these four specifically. So how do we use them in one dimension kinematics if we're only talking about either going just that way or just that way, but not a combination of the two? How do we do it? Well, let's say we have a person here. And like we said before, he has a displacement vector, right? He goes 20 meters to this right side here. And he does this in 2 seconds. How do we find the average velocity? Well, based off of what we said before, velocity, remember, is a vector. So we're looking for a vector. We need to put this in vector notation, which means it has to have direction and magnitude. And I'm going to even add something else here. It says, and find speed. We're going to find the speed as well. So the velocity would be 20 over 2, because we know that v is equal to x over t. So 20 over 2, and that would be 10 meters per second. So v is equal to 10 meters per second. That is our average velocity, but we have to add that term. This is our average speed. We have to add our direction to be able to make it a velocity. So we're saying it's going to the right. We define a normal coordinate axis of y and x. We'll say this is all in the I hat direction. So now we have a velocity. The speed would be the scalar magnitude of this, so just 10 meters per second to the right. Okay, let's do the same thing now for acceleration. Let's say you have a person here. They're starting at rest. They have no motion initially. They move 20 meters, they displace 20 meters, and they end up here. They do this in 2 seconds, and they end up with a final speed of 15 meters per second. Find the average acceleration. Okay, so what can we do with this? Well, we know that the change in velocity with respect to time, right? A is equal to dv dt is equal to our acceleration. So a equals v over t. And this little 20 meters here is to throw you off. You don't really need it right now. You could make your life harder by using one of the kinematics equations, but you don't need it. So you could just do vf, right, minus vi over the total time, which is the same thing as v over t, because this is delta v. It's always going to be delta, the change in, over the change in time. And that would be the same thing for up here. We're talking about the changes. Everything has to be a change. So delta x, delta t. So v final, we said, is 15 meters per second. And v initial is 0, divided by our total time of 2. We know that our acceleration, average acceleration, is equal to 15 over 2, and we're accelerating to the right. We see that there, so we're going to say this is, again, I hat, because we'll define this way being positive x and this way being positive y. There's our average acceleration. Let's try something now in the y direction. So we have this diver here, and he's standing over a pool. That's our pool. And he wants to jump directly into the water below. How long does it take to reach the water? So how long is he going to be in free fall for? And the only thing we're given is some variable h. So this is the point in physics where you have to start getting comfortable with working in variables only and no numbers. That is generally how a lot of physics classes will be built. You will typically not be given very many numbers, and you're going to have to do most of your deriving in terms of variables. So we're going to do this all in terms of variables. Well, what do we know? We only know we have a height. What can we do to solve for a height? We go to our kinematics equations and see what can we use in order to solve something like this. And actually, before we even do that, let me ask this. So, if we were to move, if we were to jump off this board, right, what do you imagine would happen? You assume, as you would know, you would fall pretty much straight down. If you were to just walk off, you would just fall straight down. And that's because there is an acceleration always going down, and that is acceleration due to gravity. It's also labeled as g. So there's always an acceleration going down. Always. That's just of being on Earth. You always have some gravitational acceleration pulling you down, called g. If you are going to the right, do you think if you were to just walk to the right, you would have any kind of acceleration? Would you go any direction this way, assuming there's no wind or anything like that? No. So that means we have no acceleration going in this direction whatsoever. We are solely talking about motion going down. But be aware, we do have acceleration because of gravity. So which one of these equations can we use to describe that motion? Well, we know we're going to have some final velocity. We don't know what it is yet, but we know we're going to have it. We have the initial velocity. We have the acceleration, but we don't have a time. So what else can we use to possibly solve for our final velocity and then plug it into our initial velocity, or plug it into this equation here. Well, we can actually use this formula because we have a delta x, that's h. We have an acceleration in the y direction, that's g. We know our initial velocity is 0. We know our final velocity. So we're going to have to use two kinematics equations here to solve for this. So let's do it. So now Vf squared is equal to Vi squared plus 2a delta x. And Vf is equal to Vi plus At. Equal to Vi plus At. So let's solve for the final velocity first. We can cancel out our Vi's because we know it's going to be 0. Let's do Vf squared. We know it's going to be equal to 2 times negative g, because let's define an axis here. We know that this is positive, this is positive. So this g, right, the gravitational acceleration is a vector and it's pointing down. It's going opposite of our direction of motion. So we're going to say it's a negative g. So 2 times negative g times the change in x, which is just h. That's our Vf, so we know Vf is going to be equal, and actually we're going negative h as well because we're going down, right? H is, we're not going up against this way, we're going down. So it's going to be a negative h. So Vf is equal to 2gh, the square root of that, because the negatives cancel. Great. Now we can solve for our time using this equation. So we'll plug it in. Okay, so now we're here at the square root of 2gh. We have to know that because the velocity we said is going down, right? So this is going to be negative as well. We're going to have negative square root of 2gh. Now we can plug it into this equation. So we'll have negative square root of 2gh is equal to negative gt. Our negatives cancel. And we know that our time is going to be equal to the square root of 2gh divided by g. And that's our final answer. Now, generally, a good practice for kinematics is to use a table and fill out the values. So if you're given an x, plug in an x, a Vf, a Vi, an A, and a T, and then go look for which equations you can use to be able to solve for any missing values. Typically, you'll have 3 good values and maybe 2 unknowns, and that's fine. That just means you have to choose 2 equations that can let you find those 2 unknowns. Let's do this one here. So you're launching an arrow. It goes up at some speed Vi. How high does it fly? And what's its total flight time? So if you launch it at Vi, what do we know? Well, we have some Vi, and we know that there's going to be some negative g component because there's acceleration. We also do know there's going to be a Vf. And how do I know about the Vf? I know that if I was to launch this upwards, at one point it gets so slow, right, that it starts to arc. But what happens at the top of that arc? Its velocity here is 0. And if you think about it in math terms, right, instead of just logical, you have some arc, some kind of concave function. If you want to solve for the maximas of that, you take the derivative and set it equal to 0, right? Same exact thing. So we know the Vf here is going to be 0. Now, how can we solve a time given these 3 values? Well, we can solve for, let's see, what equations can we use? We can likely use our initial Vf is equal to Vi plus At equation. So we'll have equal to Vi plus At. We know Vf is 0. We have Vi. We know this is negative g. So we have negative Vi is equal to negative gt. Negatives cancel. We have Vi is equal to gt. Vi is equal, so Vi over g is equal to t. Now we have a time. And this is the time that it takes to get to the top of its arc. If we want the total flight time, since it's a symmetrical arc, we would just multiply this by 2. That only works for this very specific case where you launch something straight up and it comes right back down. You can multiply by 2 because the arc is symmetrical. So now we have a time. Let's plug this into a different equation. Like we can likely solve for how high it goes. Let's choose an easy one. Well, we can use this last one here. That one's fairly simple. So delta x is equal to 1/2 vi, which we have. We don't have a vf, so plus 0 times t, which is just 2vi over g. So let's go ahead and distribute this all in. So we have delta x is equal to vi over 2. And this would be multiplied by 2vi over g. Our 2's would cancel. We have delta x is equal to vi squared over g. And there's your final expression for the amount of distance it would take. Now that's it. Thank you for attending.